So far, all of our analysis has been on systems that are in reduced row echelon form. What about non-reduced row echelon form? So let's say now that our augmented matrix is in row echelon form, but not necessarily reduced row echelon form. So here is an example of such a matrix. Here we have three pivots. We have a pivot in the x1 column, a pivot in the x2 column, and a pivot in the x5 column. Well, the language that we introduce for reduced row echelon form systems coherently carries over. It makes sense to call the variables that are in pivot columns dependent. It makes sense to call the variables that are in non-pivot columns free. And our language of consistency also carries over. So in this example, the dependent variables would be x1, x2, and x5, because those are the variables that occur in pivot columns. And the variables in non-pivot columns are the free variables, and that's, in this example, x3 and x4. Also, our language of consistency for reduced row echelon form systems said that the system is consistent if there is no pivot in the augmented column, and inconsistent if there is a pivot in the augmented column. Well, in this example, there is no pivot in the augmented column, so this is an example of a consistent system. So the language that we use to describe reduced row echelon form systems allows us, totally carries over to non-reduced row echelon form systems. And consequently, the Roche-Capelli theorem also carries over. So the Roche-Capelli theorem again says that if our system is in row echelon form, but not necessarily reduced row echelon form, we still have our taxonomy. Inconsistent systems have no solutions. Again, inconsistent means there's a pivot in the augmented column. Consistent systems can either have one or infinitely many solutions. And the way we determine whether or not we have one or infinitely many solutions is by looking at the nullity of the coefficient matrix. If the nullity is equal to 0, that tells us that there are no free variables, so there's not room for more than one solution. On the other hand, if the nullity is greater than 0, that means we do have free variables, and the free variables will contribute infinitely many solutions to the system. So let's finish this lecture by going through the process of solving a system that's in non-reduced row echelon form system, non-reduced row echelon form. The procedure is exactly the same, except we have to work a little bit harder now. So let's see how the procedure works. Here we have a system with two equations and three variables. This is in row echelon form, but it's not reduced. Our pivots are -2 in the first row and 3 in the second row, so they're not equal to 1. And also, as we see, above 3 here, we have a non-zero number. So this is definitely not in reduced row echelon form, but it is in row echelon form. This is enough information to apply the Roche-Capelli theorem. The Roche-Capelli theorem tells us that, well, we are consistent because there's no pivot in the augmented column. So we know that there's at least one solution. And in fact, if we look at the coefficient matrix on the left, we see that the nullity is equal to 1 because there is one free variable, and that is the variable x3. So we now know that there will be infinitely many solutions to the system. So the question now is, how do we find them? Well, let's start by writing down the equations. So the first equation should be -2x1 minus 7x2 plus 9x3 equals 12. And the second equation should be 3x2 minus 15x3 equals 6. So those are our two equations. So the procedure we use in reduced row echelon form says start with the free variables and set them equal to new variables. So the first free variable is x3. We're going to start by setting x3 equal to c1. So let's do that here. Let's replace our x3s with c1s. So now what we can do is we can work our way from the bottom up to solve for the dependent variables in terms of the free variables. This is very important that we work our way down up. Note that in the second equation, we have only one dependent variable, x2, and we can solve for x2 in terms of our free variable. And in this case, when we do the simplification, we get x2 equals 2 plus 5c1. It's crucial that we start at the bottom here, because now when we proceed to the top equation, we notice that both of the dependent variables are represented. But the cool thing about the structure here is that we already know what x2 is in terms of the free variables, so we can substitute that expression in for x2 in the first equation when we solve for x1. So when we do the arithmetic here, we should get x1 equals 12 plus 7 times x2, but we just said that x2 is 2 plus 5c1, and then we subtract 9c1, and then we divide by -2. Okay, so now we have enough information to write down the full solution. So what is the full solution? Well, we know that a solution will have 3 coordinates, but again, we don't get to fill up these coordinates however we like because we want solutions to the system. We want coordinates that satisfy both equations. So let's fill in what these coordinates are. Let's work our way from the bottom up. We said that x3 was our first free variable, and we set x3 equal to c1. So that's what goes in our solution vector. What about x2? x2 was our second dependent variable, which we could use the second equation to solve for in terms of the free variable. So x2 was dependent, and we used the second equation to solve for that dependent variable in terms of the free variable. And the expression we got was x2 equals 2 plus 5c1. So that goes into the solution vector. Finally, what is x1? Well, here after solving for x2, we could solve for x1 in terms of the free variable, and we got this expression up here, and I went ahead and simplified, and I got -13 minus 13c1. So now we have our solution vector, and we can break it apart like we did previously. We can collect all of the coefficients in a vector xp that are not attached to the free variable c1. Those are the coefficients -13, 2, and 0. So that's what goes in xp here. And then in x1, we're collecting all of the coefficients of c1, -13, 5, and 1. And so that's what all the solutions look like to the system. We have a free variable, so there are infinitely many of them. We can start with the solution -13, 2, 0, and then we can add any multiple we want of the vector -13, 5, 1, and we get a solution to the system. So once again, we find ourselves with a free variable in a consistent system, so we have infinitely many solutions. And this method is called back substitution because we started with the last equation and solved for the dependent variable in terms of the free, and then we proceeded our way back up through the equations.